So first of all, this question of looking at a situation where you're not sure whether the signals are informative or not seems really natural in some sense. At the same time, there's surprisingly very few papers that have looked into this. So as Brett pointed out, there's a paper that looks at sort of microstructure implications. There's another paper that actually empirically tried to sort of disentangle the magnitude of the signal and the likelihood that you're informed. On the partial equilibrium setting, you can basically show that if you don't know whether a signal is informative, it's going to create trend chasing, in the sense that when you initially receive the signal, you're not going to act on it. But later on, when there's public signal coming in, you suddenly are going to realize that your original signal was more informative than you thought, which would cause you to trade. And finally, there's this paper. So when we wrote this paper, I don't remember if it was a discussant or a referee that pointed out to us, oh, there's this paper, Koval, that shares some common features with your idea. So the same thing happens here. Okay, so the two papers are actually quite different, but they do share the feature that you have uncertainty about whether the signal is informative or not. And if I have time, I'll sort of try to explain exactly where the differences are, and there are actually quite big differences. But in terms of the overall idea of sort of non-informative signals or potentially non-informative signals, that paper actually has that as well. The current paper, the main contribution of the current paper is essentially it's a rational expectation asset pricing implications with risk-averse investors. And that's actually going to be very important. And that's one of the important distinctions that this paper has from this Koval paper. So let's talk a bit about the basic structure just to remind you. There's a signal. The signal can be informative or not. With probability pi 0, the signal is informative. With 1 minus pi 0, the signal is just noise. These are sort of all the shocks are normally distributed. And in the current version of the paper, mu is set to 0, and actually the volatilities of d and u are the same. And I'll touch on that in a bit. The agent receiving the signal is potentially informed. Now in this paper, the agent is confident that he's seeing the right signal. Okay? So this agent, in some sense, there's some irrationality on the part of that agent. The uninformed agent, he's fully rational. So he doesn't observe the signal, but he realizes that this signal may or may not be informative, and he updates his beliefs accordingly. Myopic mean variance preferences, which is fine. Just want to point one small point. In many of these papers, assuming mean variance preferences is exactly the same as assuming constant absolute risk aversion. In this paper, this matching doesn't work. Why doesn't it work? Because after you've observed the signal, the distribution of dt plus 1 is actually no longer normal. It's a mixture of exponentials, and as a result, this nice moment-generating function that we always use simply doesn't work. So this is a very reasonable assumption for the current paper. In terms of results, quickly, Brett went over in detail. Expected returns of volatilities are stochastic and persistent. There's price reaction to information about dividend is asymmetric. And this is the result that I at least personally like the most in the paper. And I think the authors really should sort of try to focus the paper more around this result. They do talk about it quite a bit, but I would try to make it more central. There's volatility clustering. And finally, there's a relationship between information quality of the signal and the return moments. And that depends on whether investors agree on the interpretation of the signal or not. Okay. So I'll have a few suggestions, essentially just to force the authors to work some more. So the first suggestion, I would allow for the volatility in the signal when it's informative and when it's not informative to be different. So first of all, there's no reason these two should actually be the same. But more important, I think that allowing these two to be different can help you understand the different results that you get in the static model and in the dynamic model. So they have some results that are different in the static versus the dynamic. And this will help to sort of parse out some of this stuff. So what I basically did is I solved the model for the case where these volatilities are different. So of course, all the results that I'll show you, I programmed very quickly, so all these graphs might be completely wrong, but hopefully at least some of them are right. So one important thing, let's look, for example, at how the uninformed investor updates his or her beliefs about the dividend after observing the signal. Now, why do I say after observing the signal? Because in the current paper, the equilibrium price fully reveals the signal. So you could essentially assume that this guy observed the signal. Well, with some probability, he needs to basically update the probability that the signal is informative and update the expectation conditional on the signal being informative or not. Okay? Now let's look a second in this component. So essentially just apply Bayes' rule. And the important point to note is the following. When the two volatilities are the same and mu is equal to 0, which is essentially what you have in this paper, then the posterior probability doesn't change. So essentially what happens here is they're shutting down this channel. When you observe this signal, two things happen. One is you learn about the value. The other, you learn about the informativeness. In the current version, they basically shut this down. And you can basically see that there's a simple condition that basically tells you when the signal is going to be, when is the probability going to be increasing as a function of the signal, and when it's not. Okay, so let's look at a few quick graphs. In all these graphs, the blue line is going to be the line in this economy. The red line is essentially the economy they have in the paper, which essentially what I did here is I just shut down this channel. So first thing is the probability of the signal being informative. As you see, now basically what happens is you have this U-shaped, and as you get larger and larger signals, and the reason is that sigma d is bigger than sigma u in this specific example, as you get larger and larger signals, you're more confident that these signals are informative. As a result, what happens to the expectations on dividends? Well, you get an amplification effect here at the top, and an amplification effect at the bottom. More important, let's look at the volatility of the dividends next period. Well, in the paper, you basically get this U-shaped. Now what you get is this nonlinear behavior, which in some sense is similar to what you get in the dynamic model. And now why is that? Well, in the dynamic model, you update your belief about whether the signal is informative or not when you observe D. Here, you don't need to wait to observe for D. You update your beliefs already at this point. Now what happens at this range here? Well, here basically, you're very confident that the signal is informative. So as a result, the overall volatility declines. Okay? Risk premium is impacted as well in a similar fashion. One interesting result is if you look at expected returns now have this non-monotone feature, where essentially in the mid-range you have a negative relationship, but then at the extremes actually things are quite different. Okay? Now let's look at another case, the case where mu is bigger than 0. Well, in the case where mu is bigger than 0, in this case, basically higher signals means that you're more confident that the signal is informative. Now what happens as a result of that? This graph basically shows the price as a function, again, of the signal. In the paper, they have this result that you get asymmetry where the price reaction to good news is lower than the price reaction to bad news. You see that once mu is bigger than 0, you can actually get the reverse. Now, why is that important? In a model in which the dividends are going to be persistent, next period's dividend, basically mu is going to be potentially a positive number. So in that model, potentially the result that you have is going to flip. And one thing I would suggest to the author is really to try to tease out in which situations does the asymmetry go in one direction and in which situation does the asymmetry go in the other direction. And then another interesting result that you get is in this case you get this very stark asymmetry in expected returns. So essentially when there's a positive signal, expected returns don't change a lot. But when there's a negative signal, expected returns go down a lot. And one more sort of interesting fact, you can basically get this result that when there's a positive signal, volatility goes down, negative signal, volatility goes up. Okay? And again, I think these type of comparative statics can really help the authors nail down these differences between the static and the dynamic model, because essentially the updating mechanism here is very similar to the updating mechanism that you have in the dynamic. Okay, so that's one suggestion. Next suggestion is I would try to disentangle the results that are driven by the feature that you have uncertainty about whether a signal is informative and this difference of opinion. Okay, so in the current model, you basically have these two features, and you want to try to understand what is coming from what feature and what is coming from the interaction between the two. It's actually very simple to do it in this case. Because the signal is fully revealing, you could basically look at an economy where there are only uninformed investors, and in this economy, the solution is very simple, and compare the result to the result that you have now and see which results are the same and which results are not. Next suggestion, I would compare to the setting where investors receive signals. The investors themselves know whether they receive the signal or not. Okay? Now, to do that, you have to relax the assumption that the aggregate supply is fixed. Because if you don't relax that assumption, then you could just infer from observing the action. Okay? Which leads me to the next suggestion, is essentially allow for aggregate supply to vary. Okay? Now, why is that important? I think that's important for a couple of reasons. One is it helps you with suggestion 3. The other is it really brings the model closer to sort of conceptually what they're trying to do. Because what they're trying to do is to see how you learn from prices. And in the current model, prices are fully revealing. Okay? Now, I don't think they'll be able to do this analytically, but that's fine. You know, this is a very complicated model. And the dynamic version of the model is numerically already. So I don't think there's a big cost to actually incorporating this. Well, something for future work, again, I would consider persistent dividends. The reason that I think it's interesting to consider persistent dividends is that once you consider persistent dividends, you have this effect that you get a signal today about the dividends. Next period, there's some public signal about the dividend, be it some dividend that came out or some price. You update your belief about how informative your signal was initially, and that potentially can introduce interesting dynamics. Again, I think that's a separate paper. Okay. Final suggestion, I really think the authors want to discuss in some detail the differences between their paper and this Koval paper. Okay? Now, there are a few very important differences. So the Koval paper, in that paper, there's risk neutrality. As a result that there's risk neutrality, you can't say anything about first moments. The current paper, many of the results are essentially results about first moments. Okay? Also, the mechanism itself is different. The thing that they do share both the papers is this feature that you're not certain whether the signal is informative or not, but the mechanism is very different. In the Koval paper, the mechanism is driven by some investors waiting on the sideline till information goes in their direction, and then they start trading. I would focus the paper around the results that are not present in Cow and Koval. Specifically, the fact that you have risk-averse investors, that leads to stochastic volatility in returns. That feeds back into prices through expected returns. Second, you have this asymmetric reaction to good news and bad news. That's not present in the Koval. In the Koval paper, everything is symmetric. And finally, they basically introduce a new channel for risk premium. And this new channel is essentially this uncertainty about the type of the other investors. And I would really push these 3 points because these are sort of the points that differentiate the paper from the Koval paper. How am I doing in terms of time?
About a little over a minute.
Okay, so I'll skip that. I'll talk with the authors on these later. Basically, what they do in the paper, they introduce uncertainty about the likelihood of informed traders in the market. And surprisingly, at least to me, that's received fairly little attention. The current paper, I think, takes an important step in helping us understand the implications. Specifically, it introduces a new channel for risk premium, uncertainty about the other type of investors. It highlights a very interesting channel of this asymmetry in reaction to good news and bad news. And it has some, of course, other interesting implications that Brett went over. Overall, I enjoyed reading the paper. It actually brought me back to a paper I wrote a while back, so thanks again.